So, welcome back. We have finished looking at depth first search, breadth first search and DFID. These are known as blind search algorithms because they do not have a sense of direction irrespective of where the goal is, they always search the space in the same manner. Today, we move on to heuristic search, which has a sense of direction, and we will see how that is acquired. So, this was the basic approach to depth first search. You always extract a node from the head of open, and then you test whether it is a goal or not, and other if it is not the goal, then you call the move gen function, and after doing some checks like removing seen nodes, we add them back to the head of the list, as a result of which the search behaved in a particular fashion, which we call as depth first search, I think. And we saw that what happens is that it dives into the search space till it reaches a dead end or something, and then it backtracks a little bit and again dives back into it essentially. The red node here is the goal node, and you can see that it is not paying any attention to that. The other algorithm we looked at was breadth first search, in which the new nodes are added to the tail of open, making it behave like a queue, and the consequent behavior of search was that it stuck as close to the source as possible, and we saw that this also resulted in the fact that it would always find the shortest path essentially whenever it found a path. So, these algorithms are known as blind or uninformed search methods. Both depth first search and breadth first search are oblivious of the goal. Irrespective of where the goal is in the state space, both the algorithms set out on the same predetermined trajectories every time essentially. What is needed is a search algorithm with a sense of direction. It should be in some way aware of which side the goal lies essentially and try to head in that direction. So, let us first look at something from nature, which is the pull of gravity. So, this is a scene from Lahul and Spiti, where you can see a stream flowing down a mountain side essentially. The gradient of a mountain side gives a sense of direction to the water flowing down a stream essentially. Water always takes the steepest gradient descent path. So, you can see that here it is following this path and eventually merging into a river below that. We can simulate this sense of direction in search algorithms, and that is what we would like to do. Imagine a physical agent wanting to reach the bottom of a valley essentially, and let us say that the physical agent is blindfolded. So, you cannot have a global view of the space. What you can do is that you test the landscape by taking a step in each direction and choose the direction which seems to be going down the most or the steepest gradient essentially. The question that we would have to of course address is what would define the landscape that we are traversing. Our search algorithm is, we assume that it is traversing some kind of a landscape, but how is this gradient defined essentially. So, this is what we will look at in this session. So, here is a example of how this gravity pulls the influences the movement. So, imagine that there is a stone that is rolling down a two-dimensional landscape, and you assume that this stone has mass, so that it can feel gravity and it is pulled by gravity, but it has no momentum. So, it cannot overshoot or something like that, it does not have any momentum. So, where will it finally rest essentially? So, as you can imagine, if there is no momentum and there is only the pull of gravity, then the stone will roll down this path and come to rest in a place from where all gradients are pointing upwards and there is no gradient pointing downwards. One can say that this is what it is doing, it is testing the surroundings and then follows the steepest gradient path essentially. It is also an example of local search, it looks only at its immediate neighborhood essentially. We will see how this manifests itself into a search algorithm essentially, but this idea of steepest gradient descent is one of the approaches that we will study in the next few videos. So, we have this idea of a heuristic function essentially. Testing the neighborhood and following the steepest gradient identifies which of the neighbors is the lowest or closest to the bottom of the valley. So, this notion of closeness to the goal is what we are trying to be capturing. The idea of a heuristic function is that it takes a state as input or a node as input and computes a number which is an estimate of the distance of that node to the goal essentially. If you could do that, if you could have an estimate for every node in the search space as to how close it is to the goal, then that could be used to guide search. Then the search algorithm can pick a node from open which has a lowest heuristic value essentially. Typically, we call the heuristic function as h of n, and typically it is a user defined function, because it depends upon the domain that you are operating on, and we will look at an example of a few heuristic functions very shortly. So, there are three functions that a user is expected to provide to a general purpose search algorithm. We have already seen the move gen function, which kind of navigates the space, and the goal test function, which helps it to stop navigating. And now we have a heuristic function h of n, which estimates the distance to the goal essentially. So, traditionally we do not mention the goal in the heuristic function, we just treat it as a function of one node, but in practice of course it will have to look at the goal as well. Now, since the heuristic value of the goal is going to be 0, we can say that effectively we are trying to minimize the heuristic value. So, you can see some analogy now between a ball rolling down a hill and a search algorithm following the gradient towards the lowest point in that surface essentially. So, the heuristic function estimates the distance to the goal. Now, if we had a perfect heuristic function which would be like an oracle, which would be able to tell you that what is the length of the path to the goal, then of course, our job would be very simple and the search would get guided without any looking this way or that way essentially. But in practice, what happens is that such perfect heuristic functions are hard to find, and that is why we have to end up with some kind of an estimate essentially. So, if we have such a heuristic function, how will we modify our search algorithm? We will call this algorithm as best first search. So, instead of depth first or breadth first, you are saying that look, open the best node on open next. How do we implement that? As before, we pick the node from head of open. As before, we test for goal, and if it is not the goal, we generate the new nodes. But now, the new nodes are inserted into open, which we can assume is sorted on the heuristic value essentially. So, it does not go to the head of the open, it does not go to the tail of the open. We assume that the open is sorted on heuristic value. The lowest heuristic value is at the head, and we have sorted it in increasing order, and the highest is at the tail. And depending on the heuristic value of the new nodes generated, we will insert them in an appropriate place in the open. And essentially, so with this small modification, we have changed our behavior to be a little bit more informed. the behavior of our search algorithm essentially. In practice, of course, we do not keep a sorted list, we will maintain open as a priority queue. So, this is a change that we are making in our depth first search algorithm. As you can see here, we have replaced the name depth first search by best first search. Everything else is the same in this algorithm, except that this line shown in red is replaced by the line below that shown in blue essentially. What is the line shown in red? It says that you take the new nodes and add it to the head of tail of open, because you have removed that head of open. What we are saying now is you do that, but in addition you also sort the open list essentially. So, that means this best nodes will always come to the head of the open essentially. Instead of doing this thing which is less efficient, we might say first sort the new nodes and then merge them into the tail of open, because sorting is an expensive operation and merging is a linear time operation. But as I said earlier, in practice open is maintained as a priority queue essentially. We are still using the same terminology of calling our constituents of open and closed as node pairs, but in practice we will have to modify them into triples, because we want to include the heuristic value with every node essentially. So, this is how the new algorithm looks. Everything else is different, except that now we have a triple. Instead of having a node and its parent, we have a node and its parent and its heuristic value essentially. And we assume that we can manipulate this triple. Everything else is the same, because we extract we take the node from head of open, we extract its first element, and we can do that using that built in function first. We get n, then we do the same thing. We test whether it is a goal or not. If it is a goal, we reconstruct the path, and if it is not, then we generate the children and make the new nodes and add them this thing. Here we have written it as, again, you append the new pairs to tail and then sort it. So, as I said, in practice you would want to do it as a priority queue. This is only for efficiency reasons. Correctness wise, this is fine. So, let us look at how do we define heuristic functions essentially. This is a problem that we had seen the 8 puzzle earlier. So, if you recall in the start node, so there is a blank at the top, and either the 2 can be moved to the left, or 6 can be moved to the right, or 8 can be moved up essentially. So, 3 moves are possible as shown on the right hand side, and then so on and so forth, and eventually we have some goal which is described on the right part of the screen. How do we define a heuristic function for this problem? Remember that heuristic functions are going to be domain specific, and we would expect the users to define them for us. Our job is to write the high level algorithms which will in which you can plug in any problem, and then search will take over. So, the question we are asking is, of the 3 successors that the start node has, which of the 3 is closest to the goal node essentially. So, here is one heuristic function, we will call it H1. For any node n, it simply counts the number of tiles out of place essentially. This is a bit like Hamming distance essentially. You just see which tile is in place, which tile is not in place, and add up for all the 8 tiles. A second function, which we will call as the Manhattan distance, will for each tile, it will sum up the distance to its destination essentially. So, For example, if you are looking at this tile 3 in this middle state, then you can see that it needs to move one step to the right and two steps to up. So, it is 3 moves away from its destination. That is the Manhattan distance from its current location to its destinations. Remember, the destination is in the top corner here. So, in Manhattan distance we add up these distances. In Hamming distance we simply count how many are out of place essentially. So, here is a state that we are looking at. You can see that the Hamming distance is 2. Why is that? Because as you can see, 1 is in place, 2 is in place, 7 is not in place, 4 and 5 and 6 are in place, 8 is in place and 3 is not in place. So, only tiles 7 and 3 are out of place. So, that is why the Hamming distance is 2 essentially. And if you look at the distances of how much 3 and 7 need to traverse, 3 needs to make 2 moves to go to its correct position, and 7 needs to make 4 moves to come to its correct position. So, its Manhattan distance is 6. So, these are the two heuristic functions that we have defined essentially. Now, in this given start state there are two moves possible, either you move the tile 4 down or you move the tile 8 to the left essentially. What are the heuristic values of these? If you compute them, you will see that their respective values are 3 and 7 in both the cases essentially. What does this mean? It means that both the states that we are generating appear to be farther from the goal than the starting state. But of course, we do not have any choice, we can either move 4 or we can move 8. So, we will have to choose between one of them, but this is what I meant by saying that heuristic functions are not perfect essentially. And remember that we were trying to kind of create an analogy with gradient descent, and we wanted to go to a state where the heuristic value was 0. But in both these, with both these functions, we see that the starting state is a local minimum in the sense that all the neighbors are higher than that, and gradient descent would have stopped there itself essentially. So, we need something more than simple gradient descent. So, either move increases the estimated distance to the goal. Remember, these are all estimated distances. And what do we mean by distance? Here we mean the number of moves that you need to solve the 8 puzzle from the given state. If you go to this website, whose link I have given below, you can do this 8 puzzle online essentially, and they have two kinds of representations. One is a picture and the other is a number that we just saw essentially. It does not matter, essentially you have to get them into the right place. What I want to emphasize here is the fact that when we look at these things, we are now thinking in terms of similarity instead of distance essentially. So, you want eventually the goal state, the state which is closest to the goal state is what we are seeking essentially. Of course, but this is the same example that we saw in the last slide, except that instead of numbers we have this picture of this dog here essentially. And you can think of distance function as an inverse of similarity in some sense. Of course, you have to normalize it to 1 because we want maximum similarity to be 1 and minimum similarity to be 0, but they are in some sense inverses of each other essentially. And what you are trying to do is to move through this search space towards states which are more similar to the goal node essentially. And visually you can see that the start state here is more similar to the goal than the two states that we can go from there essentially. And that is what we mean by saying that the heuristic function is not perfect, and if you have been solving the Rubik's cube, then you would probably be thinking in terms of similarity. How similar is my proposed move taking you closer to the goal state, and one of the goal states could be that every face has one unique color. So, here is another problem. This is geographical route finding. Uh, I have drawn this on a small grid where every vertical grid is, let us say, 1 kilometer or something like that, and the horizontal grid, and the start state is on the top right and the goal state is on the bottom left. And if you can see the graph, then that is a road connectivity for this particular place. You can imagine that the bluish or cyan line is a river which is flowing through the city essentially. What can we use as a heuristic function? One function is simply the distance. You just compute the Euclidean distance between all the candidate states and the goal state and choose the one which has the lowest essentially. So, we have 3 successors of the start state, and you can see that one of them has the lowest heuristic function. So, the best first search algorithm that we will see, or this gradient descent algorithm that we are looking at, will move to this node with a value of 7.21. You can also use the notion of a Manhattan distance again here. So, basically you count how many hops you are going in the vertical or the horizontal direction, going from one state to another, and you see that now you get round numbers here. So, for example, the same state which had 7 point something, now you move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps. You are 10 steps away from the goal if you were going in a grid essentially. So, it is called Manhattan distance because Manhattan is a city where the roads are very nicely laid out as grids essentially. Of course, in our graph they are not a grid, but we can still use Manhattan distance as a heuristic function. So, the algorithm that we are looking at is going to be, or we have looked at, is the best first search, and how does that operate. In this graph I have shown the state of search when the algorithm terminates. The numbers that you see in red, for example, the first node it opens is the with the one with the value 10, then the second node it opens is with a value 7, because that of all the candidates, that 7 appears to be closest to the goal node essentially. Then it goes to the third node which has a value 7, then it tries 8, value 7. But you can see that from there are no paths going directly to the goal. So, then it shifts its attention and goes to a new path, and this is how best first search will behave. It will pick up nodes in the order that are shown here in red color. So, 1, 2, 3, 4, and goal node is the 9th node that is picked up by it essentially. What I have drawn in red arrows are the back pointers or parent pointers, and this is the path that best first search would have found on this particular graph. So, here is a similar problem with a real map outside IIT Madras, and IIT Madras is at the bottom of the screen here. So, let us say you are starting at the gate in IIT Madras and you want to go to a place called Alumni Club of Anna University, which as you can see is across the river here, and this is the alternatives that Google Map has given to us. Of course, underlying this search, we will convert all this pictorial information into a graph, and that is what we are talking about. We have said that our search is going to be graph search essentially. So, again we have the start state and the goal state, and we want to find a path to the goal state essentially, and we are looking at this algorithm called best first search essentially. So, here I have superimpose the graph on the map, and you can see that what is going to happen with best first search, as we just saw in the example before also, is that it is going to drive search as close to the goal as possible till it realizes that you cannot cross the river there. In this example, there are two bridges, one is on the left and the other is on the right, and they correspond to the two paths that Google Maps is showing to us essentially. So, again this is to emphasize the fact that heuristic functions are estimates. They do not know what is happening in the completely what is happening in the domain. I mean, they can see the map, they can see the coordinates, but they can't see the river essentially, and that is why it tells you that those nodes in the red circle appear to be the nodes closest to the goal, but in practice they are not essentially, and it is very difficult to find perfect heuristic functions. So, how do the search frontiers look like for the three algorithms that we have seen? I am not included DFID here, because DFID search frontier is a bit like breadth first search anyway, because remember that DFID is basically depth first search masquerading as breadth first search essentially. So, we had seen this earlier. For depth first search, the search frontier grows linearly, shown in pink nodes on this graph. For breadth first search, it grows exponentially, shown in yellow nodes in the bottom row and the row before that. In practice, for best first search, the search frontier is not very well defined. It really depends upon how good your heuristic function is. If the heuristic function were to be perfect, then it would be linear, just like depth first search, but in practice it is not. What about the other qualities that we looked at, completeness and quality of solution? Will this algorithm find a path to the goal? Again, it depends on the heuristic function, but because it is a systematic search, remember that the only thing we did which is different from depth first search is to sort the open list essentially. And if the search space is going to be finite, then it is eventually going to search the entire space, and if there is a path, it will find the paths to the goal. The quality of solution is different, and one of the reasons for that is that our measure of quality so far is how many steps to the goal essentially. We have not given any weight to the edges. So, we are simply counting how many steps are there to the goal. So, as you can see, the best first search algorithm will head towards the goal, because it is using an estimate of distance, but in practice there might be a shorter path which is a two-step solution to the goal, and best first search is not guaranteed to find that essentially.